Good morning, everybody. Welcome back, and congratulations for waking up early in the morning to come. First of all, before I keep explaining things, I was wondering if there are any questions or comments about yesterday's lectures and the problem sheet, maybe. Everything was clear, or everything was completely confusing, so you don't even know what to ask? Oh, I guess hopefully the former.
Oh, could you remind us the relation between W and Z?
Yes, yeah. So the relation itself is not extremely important. I mean, this coordinate is the coordinate W is not extremely important to actually do any calculations, but it's very useful to visualize things because it kind of respects the crossing symmetry. But the relation is that, well, it's a relation which preserves the crossing symmetry, unlike the row coordinate, and it's Z is 1 plus W squared divided by twice 1 plus W squared. So in particular, crossing symmetry acts as Z bar goes to 1 minus Z bar, and over here it acts as W bar going to minus W bar. Okay. Any more questions? Okay, then before I continue explaining where I stopped yesterday, I think it's good to do a little recap of some of the important things, because I think especially the end of last lecture was a bit fast, so it's good to get on the same page. So the basic player in the game that we were studying is this wonderful, mysterious, magical equation called the crossing equation for the case of 4 identical scalars, where we have a sum over primaries, and here are the conformal blocks minus the cross-channel conformal blocks, so the S and T channel. And for various reasons, this equation is pretty hard to analyze. I mean, one basic reason for that is that in general the conformal blocks themselves are quite complicated functions. So you have a sum over some functions that you need to learn how to control, but we basically understand pretty well how to deal with those, even in general space-time dimension. But a more fundamental reason for the difficulty of this equation is that it involves an infinite sum over operators, and it lives in some infinite dimensional vector space. So it's an equation parameterized by Z and Z bar. So it lives in this vector space of functions of Z and Z bar, and that's really the only reason why we have some hope of constraining these infinitely many operators. So somehow the hope is that this infinity of the variables, of the operators which are, it is going to somehow cancel out with the infinity of equations that we have at our disposal. Then I talked quite at length about the regime of validity of this equation, and we learned that because correlation functions are analytic functions of the coordinates, complex analytic functions of coordinates in appropriate regimes, then not only that the equation is valid in Euclidean signature, but it can be analytically continued to the Lorentzian signature, and in general to complex variables. So we learned that the appropriate regime where the equation holds is when these cross ratios Z and Z bar are both complex and independent, and lie in this region. So the entire complex plane without this pair of branch cuts, both in Z and Z bar. And as soon as we cross one of these branch cuts, either in Z or in Z bar or simultaneously, then the equation stops being true because one of the OPEs stops converging. So for example, when we say start here, put Z here, Z bar over here, the equation holds. But maybe we keep Z bar over here and we move Z through the branch cut. Well, if we move it through this branch cut, then the S channel OP stops converging. Or if we move it through this branch cut, like that, or like that, the T-channel OP stops converging. So really, we are not allowed to only continue the crossing equation. And then to visualize this regime of validity of the equation a bit better, I use this change of coordinates that Daliang asked me about, which maps this region to a pair of disks. So we have a relation like that between Z and W, and similar relation between Z bar and W bar. And so now the regime of validity is this pair of disks, and we can somehow see nicely the various limits of the conformal bootstrap that the conformal bootstrap operates in this picture. So in David's lecture, studied the equation in the regime where Z approaches this point and Z bar approaches this point. So in this picture, it would be W approaching this point and W bar approaching this point. So that's a regime where you can actually derive some analytic results. And one comment which I made yesterday, which may have not been very clear, but I encourage you to try to prove it for yourself, is that this picture actually also includes the Reggie regime, and it corresponds to W going here and W bar going here. Now the reason why I'm saying all these things is that one important method of analyzing the Bootstrap equation was to do the most democratic thing that you can imagine, namely to start expanding from this point, which is what the numerical Bootstrap does. And one of my main points in the previous lecture was that because all these analytic regimes are visible to the numerical Bootstrap. If you go to a sufficiently high order in the expansion, then this expansion starts seeing the properties of the equation arbitrarily close to the boundary of the unit disk, and in this way, the Bootstrap function, the numerical Bootstrap functionals, can explore the regimes where analytic is available. So it would be very nice to eventually have some kind of toolkit that can maybe take the analytic Bootstrap results and input them into the numerics, or vice versa. Okay. So are there any questions about this general picture? Okay. So the problem that we are facing is that we have this equation living in some infinite dimensional vector space. So one way that we can simplify our life is to try to project it down to finite dimension. This is why we introduce Bootstrap functionals. So at the end of the last lecture, I gave you the properties that it should be some linear functional acting on the space of functions of these two complex variables, and there was the important condition of being able to drop the tails when acting on the crossing equation. So when we have such a functional, you can apply to the original crossing equation and find a one-dimensional equation now, which is just an equation between numbers, not vectors, which looks like this. Okay. Now I guess in the rest of the lecture, I'm going to use z and z bar as the coordinates to parameterize my vectors, but you can always think in terms of w and w bar. But just to unify the notation, I'm just going to write z and z bar. And then a basic. I guess I should say that we would like to understand the space of solutions of this equation, and what we mean by the space of solution is the space of allowed spectra and OP coefficients. And even for this basic equation, in general, we have no idea what the whole space looks like in much detail. So it is interesting to restrict to a smaller class of problems where you don't put any constraints on the C's, and you only put some constraints on the allowed spectrum. So we would like to understand for which choices of the spectrum that can appear in the OPE. So the spectrum would be well, we know that the set must be infinite, some set of scaling dimensions and spins, for which choices can the crossing equation be solved. Then we can make some projection to a finite dimensional vector space using these functionals. So let me give you some examples of what I mean by functionals. I mean, the simplest thing you can do is just to evaluate the equation at a point in the ZZ bar plane. I guess you should make sure that the resulting action is real, so you may need to take the real part of this or something like that. Evaluation at a point in the ZZ bar space. That's a very simple example. I mean, the example which is used in the numerical bootstrap is that the function that we have an infinite sequence of functionals, which I'm going to call omega a and b, and they are simply a pair of partial derivatives with respect to z and z bar, evaluated at the crossing symmetric point. So these are precisely the Taylor expansion coefficients around the center of the circle. And one nice property of this set of functionals is that it is a complete set. So what I mean by complete, well, I mean that if you make sure that this equation holds for all choices of a and b. So in this case, a, b are arbitrary non-negative integers, such that a plus b is odd, and also because the 4-point function is symmetric under exchanging z and z bar in parity invariant theories, and automatically in more than 2 dimensions always. We can restrict to a greater than or equal to b. So this set is complete because if we make sure that all these functionals, all these equations hold, and also the full crossing equation holds. And the reason for that, of course, is that we have complex analysis, and this is some complex analytic functions in the pair of disks. So if the Taylor expansion vanishes, then the whole function vanishes. So from these points of view, the usual numerical bootstrap functionals are very useful, but we can imagine some more complicated things, and you saw such examples in the problem set from yesterday, where one can consider some contour integrals or more general, well, some general distributions on this space. So in the example, you saw a specific case when we have a pair of contour integrals, one in z and one in z bar, with respect to some contours. So in the example from the problem sheet, the contour looked like that. Against some specific kernel, and well, and depending on the choice of the kernel, such function might answer various interesting questions about the crossing equation. Any questions so far? I guess that's good. Okay, so now let's go back to this problem where we ask for what choices of the spectrum S can the equation be solved. And for concreteness, I'm going to work in the basis of the usual numerical bootstrap functionals. I should say that this whole idea was presented first in a seminal paper by Rattazzi, Richkov, Tony, and Vicky. And this paper really started the modern surge of interest in the conformal bootstrap in more than 2 dimensions, or more generally. So, as I already started saying in the previous lecture, we can choose some 2-dimensional subspace of the bootstrap functionals. For example, we can choose the one dimension of the subspace is going to be AB equal 1, 0, and the other one will be AB equal to 1. But you could probably choose any any subset, and it will to some extent still work. And then we look at this set, and we simply plot the vectors, the vectors in this two-dimensional plane corresponding to all the vectors in this set S. There are basically two things that can happen. The first one is where the vectors lie on the same side of some line which passes through the origin. So in this case, the equation cannot be solved, simply because all positive linear combinations of these vectors lie strictly on this side, and on the other, and this line corresponds to a specific choice of a functional in the bases. So this omega is in the vector space spanned by this pair of functionals. And the other situation that can happen is when the set S looks like this, where we cannot find any plane which puts all the vectors to the same side. So this leads to a reformulation of the somehow a solution of this question that we asked, in the sense that this is really an equivalence, that if we can find such a functional, so if there exists omega such that, and now I'm going to assume that the set S includes identity, because this is what we usually require. So let's assume that S includes identity, so operator of dimension 0 and spin 0. So if we have an omega such that omega acting on the identity vector is strictly positive, and omega acting on the other vectors in the for all the other ones is non-negative, then the equation can't solve crossing. On the other hand, the obstructions for finding such a functional are precisely solutions to crossing. So if such a functional does not exist, the reason why it doesn't exist is because there is some solution to crossing. So this is, yeah. Well, I guess I can say, I guess I can just make this into an equivalence and erase the if. Sorry. Is this clear? I mean, it is not entirely clear why there should be an equivalence in the infinite dimensional setting, but this two-dimensional example clearly illustrates it. I think that this is just an example where you can't find such a functional, and there is clearly a solution to crossing. So, was there some question? Mm-hmm.
Could you repeat why the identity is the one which has?
That choice is completely arbitrary. It's just that in the case of, we could choose any vector. We just want to make sure that this equation leads to a contradiction, right? On the right hand side we have a 0, so this equation could still hold if all the functional acting on all the vectors in the spectrum were strictly 0. Right? So we want to make sure that there is at least one operator in the proposed spectrum on which the function is strictly positive, so that we get a strict contradiction. And for convenience, because we always assume that identity is always in the spectrum, we can choose the identity to play this role. Or it could be the stress sense, or it could be really any operator which you know for sure is going to be in your spectrum. Okay. So now, well, we've solved the problem, because now it can actually be put on a computer in a finite dimensional setting. So if we project to finitely many dimensions, this problem has an algorithmic solution which is provided to us by so-called linear programming. So linear programming is just an algorithm for telling us whether a functional with these positivity properties exists for a specific set of vectors. And if it does, then it actually constructs the functional. Okay. So it's solved. And this is the underlying idea of most of the initial explorations in the numerical conformal bootstrap. This approach allows a nice generalization to sets of multiple correlators and various other settings. And I'm just going to say this in words that if you want to implement the crossing equation for multiple correlators at the same time, then the relevant technique, the relevant algorithmic technique to solve it is called semi-definite programming. But the semi-definite programming also has interesting applications for, not necessarily for systems of multiple correlators, but in general. So semi-definite programming is a generalization of linear programming where this guy deals with vectors and the semi-definite programming deals with matrices. So it's in some sense a matrix generalization. Yeah. So the condition of the function being positive on a certain set of vectors is replaced with the condition of a positive definiteness of a matrix rather than of a number. Generalization of 1. Okay. Now, I would now like to discuss a specific example of such a setup in detail, which was indeed the original example considered by Rattazzi, Richkov, Tony, and Vicky, which is the problem of scalar gap maximization. So the scalar gap maximization is just a choice of a specific set S. Perhaps first I should say in words is we are asking the question, so suppose we have these two operators and we look at their OPE. Well, what does the OPE contain? It contains the identity, and it contains some scalar operators. And we are going to require that the operator of lowest dimension above identity, which is scalar, let's call it operator O0, well, maybe O1. Let's demand that the scaling dimension of O1 is greater than or equal to some number. So we are setting a lower bound on the gap. Then there are infinitely many scalar operators, and there are also infinitely many spinning operators for each even spin. So one thing which I didn't say yesterday is that in an OP of two identical scalars, there's a further restriction that not just that symmetric traceless tensors appear, but the spin of these symmetric traceless tensors must be even. So we have scalars, and we have spin 2 operators, spin 4 operators, etc. So we don't put any restrictions on these guys, which means that they are only bounded. Their dimension is only bounded from below by the unitarity bound. So this problem just translates to a specific choice of an S. Our S is going to contain the identity. It is going to contain all the scalar operators for delta. So the set is going to be labeled by the choice of delta 0, and it's going to contain scalar operators for deltas greater than or equal to delta 0. And then it will also contain spinning operators for positive even integer spin, and delta bounded from below only by the corresponding unitarity bound, which in this case is j minus 2 plus d. Yeah, and that's it. So in order, we are asking, when is it possible to solve the crossing with this gap in the scalar sector? Which means that, well, we want to find a functional which, for concreteness, again, we are going to select identity as the distinguished operator and declare that the function that we want is positive on identity, and then it's non-negative on the, well, then it's non-negative for the other deltas and j's in S without identity. And now, is there the big eraser somewhere? Okay. I guess I'm going to have to do with the small one. Very, very good. So if one works in the basis of the derivative functionals, that omega AB, then what you do in practice is that you use omega AB for A plus B bounded by some integer, capital N, because you can only put it on a computer when the dimensionality of a space is finite. And the observation is that essentially for every n which is sufficiently large, there exists, so, well, result of the numerics of the linear programming algorithm is that there always exists some critical value of delta 0, critical value of delta 0, which I'm going to denote delta star, and this delta star depends on n, on the level of the truncation, such that when delta 0 is such that when delta 0 is smaller than delta star n, the functional with those properties does not exist. Oh, sorry, this is actually strict. This is if it's less than or equal to. And when delta 0 is greater than this critical value, then the functional exists. So what this means is that in all unitary solutions of the crossing, the scalar gap cannot be too large. If the scalar gap is greater than this critical value, then that means we have excluded it, and we have actually excluded for, well, it provides a rigorous upper bound for n, and a further observation, which is a result of numerics, is that this sequence actually has a finite limit as you take n to infinity. Well, it converges to a nice, this should be kind of obvious, that delta star n goes to some limit as n goes to infinity. And well, it's easy to see that this sequence delta star n must be decreasing, because by increasing n we are just increasing the precision. So we are imposing stronger and stronger constraints, right? In other words, if we can find a functional for some small n, we can always use this functional also for higher n. It's going to solve the same problem. So that means that this sequence is decreasing. Mm-hmm.
Depend on the external dimension?
Yes, that's right. I'm gonna draw a plot soon, which that's the most famous plot, or at least the initial most famous plot of the Bootstrap. Now I guess you can say that the island has become even more famous. Okay, very, very good. Any other questions?
This statement that you make of equivalence, we cannot really use it when we do numerics because we truncate to a finite space, and just because we don't find it functional doesn't mean that there is no function.
That's right. There could, well, the equivalence is strictly true in a truncated finite dimensional problem, but the point is that a solution to crossing, a solution of the truncated crossing, is not necessarily a solution of the full crossing. Right? So if you can rigorously exclude solutions to crossing by constructing finite dimensional functionals, but you cannot be sure that these are optimal. But this is a strictly true equivalence for the abstract finite dimensional problem. Okay, so let me. I think it's kind of interesting to look at how this functional. What are the properties of this function? How it behaves? How it acts on the various vectors as we maybe change delta zero. So say we picture it like this, then let's go to a two-dimensional picture where things are easy to visualize. So this would be the identity vector, and then the identity vector is really the leading scalar operator. But now, because our set is continuously infinite, I'm not going to draw continuously infinitely many arrows on the board. So let me just draw the endpoints of those arrows. So you would typically find something like this. So this would be the set of vectors corresponding to the scalar operators, of which identity is the first one. And then there's going to be a similar sequence of lines which correspond to the spinning operator. So this would be j equal to 2. This guy is the stress tensor, because it's the first one sitting right at the unitarity bound in the spin 2 sector, etc., etc. Now, by varying delta zero in the linear programming problem, we are just really excluding a part, an arc of this whole arc from the spectrum, from S. So there are two situations that can happen. There is some critical value of there's some critical value such that if we include the identity and then the scalars above a certain delta zero and all the spinning operators, then if delta zero is in this region, then we cannot find a functional in this two-dimensional problem. So this corresponds to delta zero being smaller than delta star. But if we choose delta zero to be somewhere here, then there exists such a functional, which is just a line such that identity and all the other operators are on the same side. So this is the visual picture. What happens? It's kind of instructive to plot the action of the functional on the various operators. So let me plot the action on scalars. So this is in the case when delta zero is greater than delta star. So the function must be positive on identity, and then we demand that it's non-negative above delta zero. So it must look something like that, and then it can do whatever it wants in this region. Right? So that's what we saw here. The region of positivity is over here. So identity is positive, then there is some small region around identity where it's still positive. Then as soon as we cross through this line, it drops below 0. Then at some point, it re-emerges at delta 0, and then it stays non-negative. And the action on the higher spinning operators is analogous, except now it's non-negative above the unitarity bound. So now an interesting thing happens when you set delta 0 being strictly equal to delta star. So that's this interesting critical case. Right, so imagine I'm somewhere here, the functional doesn't exist, and now I set delta 0 to be precisely at this point. Well, that means that the functional barely exists, right? The functional wants to be this line, so that it has essentially all the operators on the left of it, but now there are two vectors. There is the identity and some scalar operator, or the scalar operator of dimension delta 0, which are strictly on the line. So let me draw this picture again. So this is the case when delta 0 is equal to delta star. Right. So the critical case corresponds to this case when we have a line. So in this case, we cannot find a functional which is strictly positive on identity and non-negative on all the other operators, but we can find a functional which actually vanishes on identity and is non-negative on the other operators. So the critical case, when delta 0 is equal to delta star, it means that there exists a functional known as the extremal functional, such that omega vanishes on identity. It's a non-zero functional, so it's an actual non-zero element of the vector space of functionals, and it is non-negative on the rest of the spectrum. And this has some pretty remarkable consequences. The main consequence is that at least in the infinite, somehow this functional knows everything about the spectrum of the theory in some sense. At least if you go all the way to the infinite n, which is hard, but so if we now look at the original Bootstrap equation, I wrote it. Well, let's use this. Let's call this guy omega star, the extremal one. And of course, you should say that all these functions only make sense projectively under multiplication by some positive parameter, because once you have a functional, you multiply by positive real number, you get a function with the same property. So you should think of the omega star is unique up to, it's possibly unique up to a multiplication by some positive number. So the equation that we get after we apply this omega star to our crossing equation looks like that, and well, we know that the value of the functional on all the vectors in the possible spectrum is non-negative. So this equation can only be satisfied if actually all the terms that appear are strictly 0. The only way that you can add up non-negative numbers to 0 is when each of the numbers is 0. So what happens is that, the reason why the functional does not exist below delta 0 is because there is some actual solution to crossing which prevents us from constructing a functional below delta star, and the extremal functional has zeros precisely at the locations of the vectors in the in the solution to crossing. So there exists a solution to crossing. Consisting of delta I, where we'll say I goes from 1 to infinity. Typically, it's some discrete set, such that the extremal functional vanishes on all the vectors. Is this point clear? Right, so now it's useful to draw again the picture of the action of the functional on the scalars again. By the way, the lecture is supposed to be again an hour and 15 minutes. So in the extremal case, we want to plot the action of this extremal guy on scalars. Well, it's 0 on identity. Then there is the critical value delta star. And now we have a solution to crossing, which consists of some scalar operators and also some spinning operators. But now I'm plotting just the action on scalars. So we know that the function must be non-negative in this region. And it must vanish over here. So the only way it can do it is if these are higher order zeros. These must be some even order zeros, assuming the action of the function is some analytic function, but it seems to be true. And there is no reason for the functional to be non-negative to the left. And typically what happens is that it looks like something like that. Yeah. So it has some negative regions strictly to the left of delta star, and it has a sequence of double zeros. These are generically double zeros because there is in principle no reason for them to be higher order zeros on the spectrum. And then when you plot the action on, for example, on the spin 2 operators, you're going to find a very similar structure, except now, well, there is the unitarity bound. Well, let me just do it for general J. So there's unitarity bound, d plus 2 minus d minus 2 plus j. And again, there is an infinite sequence of spinning operators that are a part of the solution to crossing. The function is 0 here, and then it has double zeros on the rest of the spectrum. Now, it is not necessarily true that the only zeros of the functional, that all the zeros of the functional corresponds to vectors in the spectrum. You need to be a bit careful about it, because there is, I mean, in principle, there could be an additional double zero here, which does not correspond to any vector in the spectrum, and there is no contradiction. We'll be fine with the logic up until now. And indeed, there are some situations when this happens, so we need to be a bit careful. But actually, the linear programming, not only that it gives us the extremal functional, but in the case when the function doesn't exist, it constructs for us the appropriate finite dimensional solution to crossing. So we don't have to worry too much about this problem.
Sorry? Mm-hmm. So with this method, can we also get the C5IO or
you can also get the C5IO. It's a little bit, maybe it's a little bit more complicated, but yeah, you can. So as I said, there are two different ways of looking at the problem. One is the primal one, which is to try to construct the solution to crossing, or there is a dual one which involves constructing the functional, which excludes it, and it's possible to work directly in the primal one, which constructs the solution crossing for you. So that would also construct the C's. I mean, in general, this extremal solution to crossing is unique, as you saw in this case. Well, this is a real toy example, but if we have identity and the other vector which must be included, then there is a unique way up to an overall multiplication by some positive number how to add up these two vectors to the origin. So okay, so I think this yeah.
For the spin J case, it's always 0 at d minus 2 plus J?
Doesn't have to be. You could have some solutions to crossing which don't include the stress, which don't include these. Yeah, I think typically, well, if the extremal solution crossing corresponds to a theory with a stress tensor, then it must have a 0 at a stress tensor, and it will not have zeros at a higher spin conserved currents because you don't want your, well, unless you happen to be in a free theory. Yeah, thanks. I should correct it. So in general, it looks like that, but. Very good. And now the remarkable thing is that you can actually find physical theories using this method. That was really the big breakthrough that got everybody interested in the conformal bootstrap in the recent years. So we can apply this to method to 3D CFTs, unitary CFTs with a Z2 symmetry. Actually, well, in this case, the Z2 symmetry is not that crucial, but we have two phi operators, where phi is odd under Z2. So in particular, phi does not appear in its own OPE. That's really the only way that the Z2 symmetry enters in this problem. I never know which way is the inclusion. Like this. Yeah, I think. So then you can plot the upper bound, or you can plot this delta star as a function of delta phi, and what you find is that, well, if we choose the origin to be at the unitarity bound, so in this case this would be 1/2, then you find that there is roughly speaking almost essentially a pair of two straight lines, but they're not exactly straight, and there is a kink in the bound. So this is the allowed region where the function does not exist, and in this region the function exists. So and when you look at your plot, you find there's a kink, and remarkably, the position of the kink matches very well with the scaling dimensions in the three-dimensional Ising model, specifically for where delta phi is delta sigma, and the vertical value is delta epsilon, so the energy operator of the three-dimensional Ising model. So this is telling us that to a very high precision, the solution to crossing, which prevents us from constructing a functional, when we place ourselves at the right value of delta phi, the solution to crossing which prevents us from constructing the functional below is precisely the three-dimensional, is precisely the correlation function of 4 sigmas in the three-dimensional Ising model. Then you can construct the functionals over here and approach this point. You plot them, and in the critical case, you're going to find plots like that, where to a good approximation, at least the first few operators correspond to the operators in the three-dimensional Ising model. So this is the sense in which one has solved the 3D Ising model. It's not a particularly strong sense in my opinion, but it's still very nice. That in principle, if you go to infinite precision, those zeros will, so in infinite n, those double zeros will go precisely to the scaling dimensions of the three-dimensional Ising model. So it looks like there's probably some interesting underlying structure in the Bootstrap equation, and it can motivate one to try to understand the structure of these extremal functionals pretty well. So now I guess I still have half an hour. So yeah, I can tell you a little bit about some work on constructing these extremal functionals. Mm-hmm.
In this example here, you're saying the omegas have to be 0 because all of the OP coefficients are positive to solve the crossing equation.
Yes. Sorry, can you repeat the question? I'm a bit sleepy, so it's hard for me to analyze information. Can you say it again?
So you're saying that to exclude different theories,
Yes.
you need to have all of, in this extremal case, you need to have the omega is equal to 0 on all of the values of delta.
Well, the extremal case is not really used to exclude theory in this case. It's just you can also, I mean, it's a valid functional, so you can use it to exclude theories. I mean, it tells you that there must be always, in any solution to crossing, there must be at least one operator in a positive region, or all the operators must be at zeros. But does this? I feel like I didn't answer your question, but.
My understanding of this analysis was that we always assume that because the OPE coefficients are squared, then they're always positive. But what about, can they be 0? So there could be some solutions where the function...
Well, the OP coefficient being 0 is like the operator not being there. So yeah. So it's.
So
yeah.
if you in principle had infinite precision on this omega star and saw all these zeros, though, it doesn't necessarily imply that every zero on it is the spectrum.
That's right. Yeah, that's right. That's what you were asking. Oh yeah, that's right. That is a true statement. I mean, it's a bit hard to imagine what would be some other reasons for the zeros to appear, but currently our understanding of how this infinite dimensional space of functionals is quite limited. So yeah, there could be some interesting phenomena like that. Like for example, typically there is this spurious zero over here, because typically in the extremal case the slope at identity is positive. So in order for it to have a negative region, which it must, there must be a point where it crosses 0.
You said there might be some other reason, or is there the other reason why it should appear, but why couldn't it just be dimension in some other theory, not using some other?
Yeah, that's right. It could be that somehow the same extremal functional could be simultaneous than extremal functional for different solutions to crossing. That's what. Yeah, that's right. I don't know of any examples where this appears, where this happens, but yeah, it's definitely a possible. As I say, we really understand epsilon about these extremal functionals. Okay. Yeah, I just want to make a small comment, mostly for the experts, which is kind of like an amusing connection, or amusing observation. Which is that there seems to be some small analogy between these extremal functionals and the spectral function computed by either the Euclidean or Lorentzian inversion formula. So if you don't know what these inversion formulas are, don't worry about it too much. But David is going to explain it. So I mean, this is really just a completely wild speculation or comment. So you don't have to take it too seriously. So we have some spectral function delta J, which encodes the spectrum, and this guy has poles on the spectrum. So it's going to include some poles like that for all the operators in the spectrum and the corresponding spin. And it is computed by some kind of integral kernel. I'm not going to make it precise what this means, but it's basically there is some conformal block, delta J with some funny quantum numbers applied to essentially to the 4-point function. It's really the double discontinuity of the 4-point function, but whatever. Roughly speaking, it's some linear operation applied to the 4-point function. And on the other hand, there we have this extremal functional, which has some analogous properties. So now it doesn't have poles, but it has zeros on the spectrum. And so we can maybe expect that there is some analogous operation to this one. Well, so it's not very hard to imagine that there could be that now the functional is obtained as some linear. Well, this action is obtained as some linear action on these f's. So somehow in this formula the f would be analogous to the g, and it's up it's integrated against some appropriate kernel. So the functional is defined by the kernel. You have a product of some kernel times these vectors, and it gives you a function which is double zeros on the spectrum. So these two formulas are kind of analogous. Basically, it could mean that for every theory which has a chance of being on the bootstrap bounds, there is not just the 4-point function, but there is also this special object which is the kernel in such a way that the double zeros of such an action are at the locations and are at the points in the spectrum. But this is really just a random, very speculative comment.
Can you make it more precise in the case of generalized free field? Because you have exclusive functional.
Yeah. Well, no, not really, not really. Well, I can make it. I can tell you more after the lecture. Yeah, but I think the message of this is that the 4-point function of the 3D ISA model is a very complicated thing, and you wouldn't expect that the extremal functional is simpler than that. I think that whatever the extremal functional is, it's a very complicated object, at least as complicated as the 4-point function. No, I think it's not for the generalized free field, as far as I know. In which case, we actually know what the omega is as a function of delta. Now, also the zeros are double zeros in this case, whereas in this formula.
In this form, can you write for the free functional? Can you tell me what the k is? Is that what you're saying?
I can tell you what the k is in 1D for the generalized free field, and it's definitely, it looks more complicated than the 4-point function of the generalized free field. And this is not 1 over c squared, but I think that doesn't kill this kind of idea completely. Who knows? Okay, so yeah, in the remaining 15 minutes, maybe I can tell you a little bit about some actual examples of extremal functionals. So as I said, you in all the examples that we have tried, you only get the optimal bound once you take n to infinity. So infinitely many derivatives, which basically means that the functional wants to see all the way to the boundary of the crossing region. Right, and I have these two disks, W and W bar. I expand over here. So for example, when I Taylor expand, when I want to know what is the value of a function over here, well, I need to Taylor expand, and Taylor expand is going to contain infinitely many derivatives. And somehow the further away to the boundary I want to see, the more important the higher derivative terms are going to be. So this is telling us that maybe, even though thinking in terms of derivatives is very practical for the numerical purposes, it may not be the right way to think about these functionals analytically. And what seems to be working is to use some ansatz for the functionals in terms of integral kernels. And this has not been made well, to some extent you saw examples of this in the problem set from yesterday, where we had a pair of contours in the z and z bar, and that was kind of useful for solving the free theory. But the problem of actually constructing the function with double zeros is more complicated than just than what you saw. So this hasn't been really made precise in more than one dimension, where we have two complex variables. But it has been made more precise in 1D, where, well, what is the setup? We still have a 4-point function for identical scalars at 0, 1, and oops, what did I do? This is 5. And 0, z, 1, and infinity. And the correct picture for the crossing equation is that instead of one disk, so instead of two disks, we have the complex region of z, where the Euclidean configurations correspond to being between 0 and 1. But you can go to the entire complex plane, for example, by considering out-of-time order correlation functions. So specific choice, well, one specific choice of an out-of-time order correlator at finite temperature is going to take you on this line, and the limit when the imaginary part goes to infinity is called a chaos limit, which is somehow analogous to the Reggie limit in 1D. And actually, in one dimension, there was a good guess for what the exact upper bound is for this problem. Namely, the numerics is indicated that the delta star is equal to 2 delta phi plus 1, which is the gap in the theory of the generalized free fermion. Where the 4-point function, now the 4-point function is just a function of z, and it takes the following form. So it's given by this in the Euclidean configurations and by unlike continuation everywhere except for these two branch cuts. And the spectrum over here, the spectrum of this, when you expand this in conformal blocks, which you can try for yourself, it's a nice exercise. You'll find that the spectrum, well, it's identity, and then it's 2 delta phi plus 1, that's the first operator, 2 delta phi plus 3, etc., etc. You can think of these as two particle states where I have two psi's and I'm hitting them with a bunch of derivatives, with an odd number of derivatives because they are identical fermions, so you cannot have an even order derivative here. And then it actually turns out that it's possible to so it turns out that this guess for the optimality of the generalized free fermion is correct, and you can actually prove it by constructing the exact analytic functional. Yes. Mm-hmm.
Is it really minus in front of vector? What's the type?
It's minus. It will be plus in the generalized free scalar, and the generalized free scalar has a different spectrum. It would have 2 delta phi plus even integers, and the generalized free fermion has odd integers. In this case, there is no contradiction with, well, you may want to complain that we started with phi being a scalar primary. So why are we suddenly having fermions? And there's really no contradiction because at no point are we really exchanging any operators here. We are, well, in one dimension you have no spin, so this is not a fermion in the sense of an half integer spin particle. It is a fermion in the sense of the statistics, but we are only staying in this region where, yeah, we are always staying in this Euclidean region. Unless going out of time order, and then you cannot really tell whether the particle is a fermion or a scalar. It's a consistent solution to crossing, to the origin, to the problem which I wrote at the beginning of the lecture. So here what you find is that you can actually construct the optimal functional. It looks so in the W plane now, where let me remind you that z is 1 plus w squared. Well, this is maybe not so important, but in this picture, well, okay, I can motivate the shape, the way the function looks by saying some words, but I'm not sure if that's really legitimate. But somehow the analytic bootstrap works around the double 8 cone limit and the Reggie limit, and here the analog of the Reggie limit is the chaos one, so it's kind of this point. Whereas the numerical bootstrap starts here. So, and it turns out that the optimal analytic functional somehow connects all of these together. That it can be written as a pair of contour integrals, where one contour stretches from this numerical bootstrap point to well, to the OPE point, and another contour stretches from the numerical bootstrap point to the chaos point. And I mean, if you don't understand what this chaos limit is, don't worry. Perhaps Joao might talk a little bit about in this lecture, or you can read about it. Well, oh yes, sure. Sorry, I should. I mean, the precise shape of the contour doesn't matter because everything is holomorphic, but the endpoints are important. So there's a pair of contours, one which goes like this from the crossing symmetric point to 1, and another one which goes like this. And the optimal functional, so the W star, acting on some general test function. It is a sum of two pieces, one which goes from 1/2 to 1, and it's an integral against some holomorphic kernel, which I'm going to, sorry, I want to call it the other way. So one kernel which I'm going to call g of z against this test function, and another one which goes from 1/2 to 1/2 plus I infinity dz f of z. And well, you can actually fix these functions analytically. They take. Well, we have a pair of such functions. Yeah, we have a pair of these functions for every delta phi. For general delta phi, they're a bit complicated. There are some hypergeometric 4f frees, but there are some just to show you that they are not always completely crazy. At least for some special external dimensions, they can be quite simple. By trial and error. Well, you can, in principle, you can start from the numerics, and then you compute the functional in terms of the derivatives, and you find that these coefficients converge as you increase the truncation, and then you might see. Well, this is not how it was found, but you might be able to re-express the functional written in terms of derivatives in this form. So this is actually equal to some sum over j from 0 to infinity of some numbers alpha times the 2j plus 1 derivative in terms of w. So there are, you can express it in this derivative form, or the way this was actually found was by trial and error. You try, and you know that you must construct a functional that has double zeros on the spectrum of a generalized free fermion, and this imposes pretty strong constraints on these functions, g and f. And it looks like the same ansatz for some g and f works for many other one-dimensional problems.
Is there a way to all around or build this extremal functional?
Sorry, is there?
I think you want to build an extremal functional, but is there a way to auto build or to calculate all of this alpha as coefficient?
Order by order, maybe there could be. I haven't really thought about it. Like, you could try to impose that you have a doubles. You can try to impose that you have a double zero up to a certain double twist operator, and this is going to give you a set of linear equations for a finite number of alphas. But this is not how it was found. It could be. It could be tried. And in some cases, these functions are quite simple. So for example, for delta phi equal to 1/2. You find that this works. So it's actually a rational function. And G is related to F by some symmetry. It's just -2 times something like that. Okay, so it looks like, at least for the, I think it's certainly true that the simplicity of these kernels is due to the simplicity of the underlying solution to crossing, because it's a generalized free fermion. But perhaps this technique of analytic extremal functionals could be useful in other setups. Like in particular, because it looks like the extremal functionals definitely sense the analytic regions. So you would expect that in the extremal case, in higher dimensions, there's also going to be a piece of the function which probes the double-eyed cone limit that David was talking about yesterday. So there's maybe some space for some combination of analytics and numerics where you input you input what you know from the analytics and the double-eyed cone limit into the construction of the functional, or vice versa. Yeah, I still have 5 minutes, but I don't really want to go into more detail, so I guess I'm going to take questions.
So the statement that gap is that of the generalized free formula is true for what values of delta phi?
It's true for all physical values of delta phi. So that's all positive delta phi.
This seems to conflict with the tensor model results.
Uh-huh.
What's the story there?
Isn't there, well,
So this seems to conflict with the tensor model results where delta phi is, 1/q. And in those theories, the first operator appearing in the 4-point function is dimension 2.
But you have flavored symmetry in that case.
yeah.
So is that the resolution?
Well, I guess what must happen in that case is that there's always going to be one representation of ON, which is below or on the generalized free fermion. In that case, you're importing more symmetry, so the bound must be stricter. But the bound, when averaged over all operators, well, when superimposed over all operators, right? There's going to be some scalars, tensors, and symmetric and antisymmetric, and the claim would be that at least one of these three operators must always be below or on the generalized free fermion. If that is true, then there is no contradiction. Do you remember what the bounds in the three sectors are? Perhaps you mean that the bound is above if you look at a scalar sector. Yeah, but if you look at symmetrics or antisymmetric, maybe the bound is below. Yeah. Okay, of course.
In the homework, you were saying that like these functionals should have some properties that you can exchange some with integral.
Yeah.
Like, is there analogous things known for higher dimensional case? Like if somebody comes up with some of these?
Yes. Yes. Well, the general rule I gave you in the previous lecture is just that the action of the functional on the tail of the OP expansion must go to 0, and then, well, if you have some specific ansatz for a functional, say in terms of contour integrals, you may want to impose this condition on the kernels appearing in the contour integral. But yeah, typically it's always tied to the behavior of the tail on the boundary of the convergence region of the OP expansion. There in the homework or in the exercise, the problem was that the contour was approaching infinity, which is already on the boundary of the convergence region, which is why there is a condition there. And in this case, there are 2 points where the action of the functional somehow approaches the boundary of the crossing region. It's here and here, and correspondingly, you need to impose some softness properties on the functions. I guess here it means that f of z. So f of z is like what you saw in your homework, basically. F of z in this case must be of order -1 minus epsilon, which indeed it is for positive epsilon, which indeed it is because this one goes like 1 over z squared. And you can now when z goes to infinity, this guy. Okay, I think I probably screwed up here. And this goes to, well, anyway, you have an analogous condition on the g around here because it approaches the boundary of the crossing region, and it can be worked out from knowing the OP convergence property, how fast the OP converges.
Suppose you make some arbitrary stricter assumption on the spectrum. Say you impose a gap, say on the spin 2 sector above. You will still find a different bound. Can you still construct extremal functionals for this new boundary and maybe learn something?
Well, at the moment, so you only have spin in higher dimension. At the moment, no one has constructed an extremal functional for any higher dimension, not even the scalar one. Numerically speaking, yes, yeah, and the bounds are interesting. You can see you can see the 3D or 2D Ising model also by bounding, by making a bound in the spin 2 sector. So let's say you don't impose anything in the scalar sector, and you just impose a gap above the stress. So you say there is a stress tensor. Now stress tensor plays the role of identity, and you impose a gap above stress tensor in the spin 2 sector. And by maximizing it, you can see the 3D Ising model even more sharply, because now not only that there is a discontinuity of the derivative, but there seems to be almost a discontinuity of the actual bound. So the bound looks like that as a function of delta phi. And the stress tensor is here. So the stress tensor has a big gap in the spin 2 sector. This is like 2. And this is the second spin 2 operator in the 3D Ising model. So yeah, you can do various things. But this could be an even sharper way to see the 3D Ising model. Mm-hmm.
For the extremal functionals, you kept saying that you sort of expected them to be double zeros. Can you elaborate on why it can't be higher order?
There's no argument. In examples, it's true, except for some very special cases. But yeah, it's true in examples.
Sounds like a pretty strong statement. Every zero is a double zero.
Yeah, I guess it's not always true that there are some special maybe values of delta phi where one of the zeros becomes higher order. There are like some phase transitions phenomena. But, no, it's not always unique. It's not unique for the 4D free theory. Yeah.
Also, do you like if you separate in this formula for the free fermion, if you separate out the identity, do you see like an easy way why this one is working?
If you separate out the identity.
You found a functional that has double zeros exactly on the spectrum. Usually the way I think about it is like, it acts on the identity. I have a functional that acts on the identity, and on all the rest it's positive. Can you see like this acts on the identity, gives you something,
Well, the extremal one is completely democratic. It's 0 on identity and 0 on the rest. Otherwise, you would get a contradiction with crossing.
Does that let you like do perturbation theory around it?
Yeah, there are some. Yeah, you can actually use these functions to compute loops in ADS. I could do perturbation theory around the generalized free fermion to relatively high orders in some cases.
Is it written out somewhere?
Oh, it should appear soon. Yeah. Okay, I think I'm over time already. So thanks for your attention and for the great questions.